Well, a warm welcome and good afternoon to our August bite-sized corrosion series, where we're looking at the impact of contamination of our waters. We're trying in our bite-sized corrosion series to make nuggets of corrosion-related information accessible and available to our audience to help you to understand some of the corrosion experiences with which you might find yourself exposed. Now let's get on to today's topic. During our first session yesterday, we had a quick look at water and some of its properties that can cause it to be corrosive. Today, we're going to continue our discussion looking at perhaps one of the most well-known and perhaps one of the least talked about contaminations, the kind of hot potato, as it were, of acid mine drainage. And for the longest time, there has been one name synonymous with keeping our attention focused on the important topic of acid mine drainage, or AMD, here in South Africa. And that is our environmentalist, Professor Anthony Turton. And I am delighted and deeply honored that he has taken time out of his schedule to chat with us on bite-sized corrosion. So welcome, Anthony, and thank you so very much for joining us today.
Thank you very much for having me. It's always a pleasure to share what bit of knowledge I have on the topic. It's a very fascinating field, and it's a field that's filled with lots of counterintuitive realities.
Indeed. And just for our listeners, Prof. Anthony is based in Perth in Australia right now. But as we get started today, Anthony, perhaps a good place to start would be a brief summary of what is this AMD, a kind of AMD for dummies, as it were.
In South Africa, we've built our economy on mining. The last century was the century of mining, and we've been mining a number of different minerals, most notably gold and coal. Those are the two most important. There are others as well, but those two ore bodies are very, very closely linked to acid mine drainage. So what is acid mine drainage? Both of those ore bodies, both coal and gold, are laid down in pyritic ore bodies. So where you get iron pyrite in the ore body, that ore body was laid down at a period of geological time when there was no atmospheric oxygen. So it was the absence of atmospheric oxygen when the pyritic ore bodies were laid down that resulted in iron and sulfur coming together to form iron pyrite. So the pyrite in the ore bodies, when it comes into contact now with oxygen, it starts triggering a chain reaction that is unstoppable. The sulfur part of your pyrite starts oxidizing, forms a sulfate, SO4, and sulfate, when it comes into contact with water, H2O, you start getting the formation of acid. Think of it as a fire in the rafters of your roof, but once it starts, this fire produces its own oxygen. So you can't smother it, and that's what it's all about. What makes it interesting is that while we were in an active mining phase in South Africa until the latter part of the last century. We had a very aggressive mining phase. It was never a problem because there was active dewatering taking place in all of the mines. But now in the post-mine closure era, when those mines are no longer economically viable, the void is flooded. And once the void gets flooded, there's still many pillars left in the ore body. These pillars are structural pillars. They hold up the roof. And of course, those pillars have got very high-grade ore in them, and they start oxidizing, and you start getting the formation of acid mine drainage. And that only became a problem in 2002, thereabouts, when the mine void in the western basin of the Witwatersrand completely filled up to what is known as environmental critical level. It reached the environmental critical level, and it started flowing out to surface at a place called 18 Winds Shaft, which is a ventilation shaft in the old West Rand Consolidated mine. And it flowed into a little river called the Tweeloopie-Spruit, and eventually into the Crocodile River, into Hartbeespoort Dam. It became just another one of the many polluters in Hartbeespoort Dam. And that became just a national crisis. And I was brought in as a consultant at that point in time to advise the chairman of the board of an Australian-based mining company that had that mining right at the time, and they were plunged deeply into this crisis. And that's what brought me into the sort of epicenter of rethinking, what acid mine drainage is and how do we understand it and how can we mitigate it and know what it's all about. So that's kind of what it's all about. So bottom line is South Africa is very severely impacted because of the Mpumalanga coalfields. So the entire Mpumalanga that used to be a maize-producing province But you can't produce maize anymore. Once you've got acidic water flowing, there's all kinds of chemistry that happens that causes your food production to not be sustainable. And of course, we've also got the gold, and with gold, the viticulturists from gold fields are now no longer economically viable. There's just one or two mines still functioning. And of course, we've got this massive amount of tailings on the surface. And the unspoken hazard there is uranium. We've got 600,000 tons of uranium tied up in the mine dumps of the Witwatersrand from gold fields, and all of that now is starting to react to the changing chemistry. So we've now got the situation, the unspoken of thing is this. Johannesburg is very possibly one of the most uranium contaminated cities in the world. And that's the big scandal. And you aren't allowed to talk about that, because if you do, it becomes a career-ending move. Ask me and I'll tell you about how that works.
Okay, well, we'll try not in any careers today, but you alluded to the fact that it sort of precipitated in the early 2000s. And I remember clearly, I suppose, in the sort of, I think they called it the noughties, in the first sort of 10 years of this century, how prominent AMD was. And in fact, you shared an incredibly well thought through paper about 10 years ago, debunking some of the myths about AMD. I guess the question is, have we made any progress between then and now, sort of 10, 12 years down the line? And I'm hoping the answer isn't going to be too negative.
Okay, well, at that point in time, there was a general panic over the acid mine drainage story. There were sensationalist articles being published. I mean, one of them, a journalist took what I said completely out of context. At that stage, I was the spokesperson, the media spokesperson for the CSIR. And that meant that I was in front of cameras or in front of journalists, every day of my life. One journalist took the thing out of context. She asked, does acid mine drainage corrode metal? I said, yes, it does. And then she sort of extrapolated that to say that structural steel in buildings, the rebar, is going to cause the high-rise buildings to collapse now. That, of course, is entirely untrue. So there's been a lot of damage done by that sensationalism. However, having said that, we've now got a very, very profound insight into AMD. And it's become a very counterintuitive thing, because it's not really the water that bubbles out of the ground team wooden shaft. That is not the water we've got to worry about. There's a certain set of reasons why that is a very precise problem, but that's not a structural problem, for your buildings. When you go into corrosion, into structural elements for buildings, there's a different set of problems. So we need to apply our minds in a very cold and sober way to understanding the pathways of the corrosion problem. All of these things are ultimately soluble. That's the good thing about a problem. Problem is, once you've defined it properly, you can solve it. And at that stage, it was a dilemma, not a problem. So the paper you referred to, when I debunked the myths, was just to try and get some focus onto, well, what is the problem? And the problem is actually not the water coming out of the void. That's a relatively small and easily managed problem. The real problem is the non-point source pollution caused by the presence of the many mine dumps. And of course, from a corrosion perspective now, where you've got buildings that have been built adjacent to these mine dumps, or in many cases now, some of the mine dump land has been recovered. So you've got factories that might be made of steel structures or what have you, that have been built on top of the footprint of the old mine dump. There you've got a very unique set of problems that have flown under the radar screen simply by virtue of the fact that all the hype was about the water flowing into the rivers, and that's the least of our problems. That's sort of where it came down. So in that particular paper, what I did was I just came up with the notion of flow pathways, and we've got to understand the different flow pathways, and we've got to understand the genesis of the problem. And the genesis of the problem is actually rain that has got a very low pH. So it's acidic rain that falls on top of the flat tops of your mine dumps. And your mine dumps are tailings dams, they're dams. So the flat top actually captures the rain at low pH. And because the dump consists of pyrite, the pyritic material I spoke about earlier on, it starts reacting with that pyrite, and you start getting an acceleration of the acidification process. But then you say you had a discussion yesterday about some of the principles of water, and you mentioned a couple of things now, but there's a new thing I'd like to add, and that is it all comes down to pH and EH. So EH is the redox conditions. In other words, is it an electron donor or is it an electron recipient? Redox conditions and pH. Once you understand those two variables, then suddenly, bingo, you could start going into very deep and profound insight into what happened. So get back to the mine dump now. The acid rain falls on top of the mine dump. Mine dump's made of pyrite. You get the reaction occurring. It accelerates the change in pH. It becomes extremely acidic. And anything below a pH of about 5, uranium starts becoming mobile. And in the mine dumps, we've got 600,000 tons of uranium. So that uranium starts concentrating, and you start getting this crust of uranium that starts forming. It leaches, basically. And then you go through a series of wet and dry desiccation cycles. It gets wet and dry and wet and dry. And each of those, you now get a movement of this acidic material, but now it's uranium rich. And of course, that becomes another problem in its own right. So once you understand the pathways and the fundamental processes that drive it, then you can start intervening from an engineering perspective. So that's really what that paper was all about, just to try and help us to understand that there are a number of pathways. Each is unique and specific, and each has got its own specific intervention. And that's really what it was about.
Excellent. Well, thank you for clarifying. And Prof. Anthony has very kindly made that paper available, and we'll upload that on our website so that you can read it. Certainly something you need to give some attention to. It's not light reading, but it was certainly very interesting reading. So thank you for that. I just wanted to go back to this concept. So as you've rightly said, that instead of panicking about the water, we should be more panicking about the slime stands or the tailings and post-processing those. I mean, a number of the dumps have now been post-processed. Are they processing them only for gold, or have they found ways to extract the uranium? I mean, if that's the problem, can we not get rid of it?
Yes, okay. So let's just go into some fundamental principles involved there now. So firstly, for every ton of gold that was removed over the last century and a half, between 10 and 100 tons of uranium has also been removed. So depending on the reef body, and this is what you need to understand, each reef body has got a different configuration. No two reefs are the same. So that's an important thing to understand. So the reef bodies that you find in the Western Basin, in other words, the Western Basin of the Witwatersrand Goldfields, which is really around Krugersdorp, Randfontein, that area is very rich in uranium. So as you go further east towards Springs and whatever, you've got less and less uranium because there's different ore bodies involved. So the West Rand is where, of the 600,000 tons of uranium, 400,000 tons is found just in the Western Basin. And in fact, it's found in 3 different dumps. There are 3 physical dumps that have got most of it. So, once you understand that, then it's a different animal that you're dealing with. But you must also appreciate that when the gold was originally processed in the late 1800s, early 1900s, the processes, the metallurgical processes were fairly unsophisticated. So there was a lot of residual gold left behind. So just to get back to the current tailings composition, for every ton of tailings, depends where you are, you've got about 1/3 of a gram of gold, and you've got between 10 and 100 grams of uranium.
Wow.
So you still got a lot of uranium, but if you take the Western Basin dumps, where you got 200 grams per ton of uranium, that is as good as any uranium ore body where they're mining uranium, anywhere else in the world. So we could conceivably mine it, and I wish we would. It would make a lot of sense to do it. But for whatever reasons, we've not got around to it. There's a whole lot of politics around that, but that would be a good thing to do.
Yeah, to me, it would solve several problems. Income, relatively easy, you're not going underground, and of course you're removing the uranium from this acid mine drainage water that is problematic.
Yes, so we get back to the sort of the basic principles that I explained just now. So you get EH and pH. So is it the redox conditions are one of the defining factors, and then the pH, anything below a pH of 5, then certain things happen. When you start going sort of above a pH of 5 to about pH of 10, then different sets of things happen. So you need to understand that as a point of departure. And then from there, you've got to understand now, are you interested in what this will do to concrete, for example? Are you interested in what this will do to rebar? Are you interested in what this will do to structural steel, or to pipes or whatever? Each of these things have got their own different challenge in it. But it all comes down ultimately to the fact that we've got sulfate being produced. That sulfate is causing an acid to happen, and then the acid drives all kinds of chemistries. And if it's electron donor or electron recipient, the redox condition, you get different sort of outcomes happening there. And that's really what it's about in its most fundamental, in its simplest form.
Yes. Now, obviously, the movement of this water is also going to impact the soils in the vicinity and change their natural status, if we can call it that, and make just the soils more corrosive.
Yes, so I mentioned earlier on now that Mpumalanga, where the coal fields are, used to be a place where we produced lots of maize. Now, what's interesting about maize is that maize is extremely sensitive to certain metals in the soil. Now, all soils have got metals in them. It's a common thing. And the good thing about chemistry is that when you tend to be on the neutral part of the pH scale, then most of those metals are tied up in some mineral form or other. They compound, or they're not accessible. They're there, but they're not hazardous.
Yes.
But now, one of the metals in our soil quite universally in South Africa is aluminium. Aluminium is we get very low grades of aluminium throughout all the soils, and aluminium is highly sensitive to pH. So our biggest risk in South Africa, from an acid production perspective, is not acid mine drainage. It's actually acid rain, because acid rain is being put out by the Escoms and what used to be the ISCOs, the ArcelorMittals, etc. So in other words, atmospheric pollution caused by sulfur dioxide. Sulfur, once again, sulfur combines with oxygen, forms sulfate, and you start getting this massive amount of sulfur production. And what's happening now is acid rain falling over the maize fields starts dropping the pH of the soil quite dramatically, and aluminium is released, and aluminium becomes toxic to two different organs in the maize plant. The root itself, the root tip itself, is very sensitive where the cells are dividing, where you get active growth there. Think of a stem cell in a human being. It's like a stem cell there, where you get cells that are undifferentiated, becoming specific organs over time. They are stunted, so your roots remain stunted. But then you get, at the end of the maize cob, the millie cob, you get those hairy tassels that stick out the end of the millie. Those are hollow tubes. Those hollow tubes need the pollen to travel through the hollow tube, and those hollow tubes become bumpy. They become all knobbly, and they're no longer smooth hollow tubes inside because of aluminium toxicity. So your maize becomes impossible to fertilize. Pollination doesn't occur. So what happens is you now start getting a drop-off of your maize productivity. But what you then do, if you're a farmer, you now are obliged to put down calcium carbonate. So you neutralize it. You neutralize it with calcium magnesium carbonate, agricultural limestone, and then your calcium starts becoming toxic. Then you start getting a buildup of a whole bunch of other unintended consequences. I spoke earlier on about that speciation chemist colleague of mine. We were working on this thing for the sugar industry, where you get corrosion in falling form condensers for your calandria tubes for your processing plants. And that's also to do with the fact that excessive calcium has been placed on the soil over time. And therefore you get oxalate, you get calcium oxalate being formed. And calcium oxalate is nature's way of dealing with toxic levels of calcium. It sequesters it as an oxalate. And oxalate is extremely hard. It's kidney stones are made of calcium oxalate. It's one of the hardest known substances, but it all comes down to the fundamental chemistry. So when you start fiddling with acid mine drainage and acid rain, in my professional opinion, from a national risk perspective, acid rain is far more serious than acid mine drainage is, and yet neither of them get the attention they deserve. The one will ultimately result in the collapse of our food supply, but that's an agricultural problem, and then the other one, ultimately it becomes a structural engineering problem and a process engineering problem.
Yeah, and I can see that it fits into different categories or boxes and is easily shunted around on the political front, and solutions aren't made. And I think I know the answer to this question, but I'm guessing there's not a lot of funding available for research to try and solve these problems.
Well, you see, the funny thing was the mining industry tended not to want to talk about this problem. In fact, we get back to the 1940s, 1930s and 40s when uranium started becoming relevant, when the atomic bomb was being produced. Some of the uranium used in the atomic bomb, used in the Manhattan Project, came from Krugersdorp. Krugersdorp used to be called Uranium City. So it was classified top secret. So you try and find a thesis written on it, and you'll find they're all classified, they're gone. You can't get access to them. So because uranium was this classified mineral, The mining companies don't want to talk about it. There's now an embedded liability. So there's a vested interest not to talk about it. And therefore, there's been very little funding that's come available. And in fact, it's become so politicized that if you are foolish enough to dabble in that space as I did, then you're going to get your fingers burnt and you're going to get pushback. But the bottom line is that it's a serious issue. It's not going to go away tomorrow. There are structural issues, there are engineering-related issues, there are building management issues, the human health issues, and of course now of late you've got human settlements adjacent to mine dumps. You've got the last count that I had was probably something in the order of about 1.5 to maybe 2 million people that are living in close proximity to contaminated land, from mine dumps. That's a serious problem. I was involved in a project for the Gauteng legislature to help them to understand the risk of, they wanted to develop what they call mine residue areas, which is the area around your mine dumps. They wanted to develop that into agricultural land. And we did a big sort of study, an in-depth study of that. And when Nomvula Mokonyane was the premier, and we alerted them to the fact of all these hazards, and they just buried the report. The report just buried, just was taken out of the public domain and just never saw the light of day again. So the problem is just perpetuated. More and more people are settling on that land. Where you've had very successful removal of the tailings dams, particularly out in the East Rand, a lot of mine dumps have been cleared there, and a lot of industrial land has been made available. And I personally support that. I think this is what we should be doing. But you can never decontaminate the land fully. There's always quite a serious reservoir of sulfate in the ground. So you have to design your buildings, and you have to have a long-term corrosion management plan in place, and would hopefully start off with a good design. And then thereafter it probably gets easier if your design is right.
Well, and clearly it's bigger than just corrosion because it impacts our lives as well. So that is quite sobering. I cannot believe how time has flown, and we're almost out of time, which is tragic because this has been such a fascinating discussion and I've learned so much. And the big panic about AMD is possibly less of a panic, and environmental pollution being something that we should focus more attention on is something that I really value and take away from this conversation. So thank you so much, Anthony. And I do hope our audience has enjoyed this discussion as much as I have. I hope you will all take away with you today the concept that as long as we can define the problem, there's definitely a solution, and that's always very encouraging. Thank you, Anthony, so much for being so willing to chat with us as you have.